Okay, so here's a little intro for the labs because we've got a lot of data to collect. I want to make sure we have enough time. So there are two labs. One is a vibrating string. So what we have are two stands, and then we have like a little member that sticks out here like that. And so we tie the string to one end here. Actually, on this end, we just tie to the pole. And then this one goes over this part that's sticking out. And there is a way to attach weights. So what this is to do is to change the tension in the string. Now there's a length. So the length that we'll use for the vibration calculations is the distance between this stand and where the string goes over. So there's some additional string that hangs here, but that doesn't affect the vibration characteristics. So the things that we need in terms of vibrating strings is we need the length in meters, we need the tension, and the tension, what we can do is we'll take the mass that's hanging and multiply by G. So we're going to have 4 different masses that we're going to do. We're going to do the hanger by itself, which is 50 grams. Then we're going to add 100 grams at a time. So these are the four masses that we have. We'll convert that to kilograms, and then we'll multiply by 9.8 to get the tension in the rope. Okay, what else do we need? We need the mass per unit length. So here what we're going to do is we're going to measure the length of this cord that we use, and I'm going to do this for you. So this is going to be fairly long, like 10 meters or something like that. And then I'll measure the mass, so we'll call this small l. We'll measure the mass of the whole thing, so the mass per unit length is the mass of the entire cord divided by L. Now what happens though when you put these masses on, this cord is going to stretch, and so when it stretches, the mass per unit length is going to go down. So we're going to measure the unstretched length. So this is the unstretched length from here to here, and then we'll measure the length from here to here and the amount that this part stretches. And that'll give us the total length of this, both unstretched and as we stretch it. And that as I put more mass on, this thing is going to go lower. And we'll be able to calculate the mass per unit length. So this is not a constant. This is actually going to, as mass goes up, this is going to go down because of the stretch in the string. Okay, so I'll explain all that. Then what we're going to do is we have a little speaker here that will move this string up and down. And we will vary the frequency of this input oscillation. And first thing we'll see is at some frequency we'll get the first harmonic, and it'll be pretty obvious. We'll record that frequency. Then we'll get the second harmonic, which will look like this, and we'll measure that frequency. And we're going to measure up to 5 harmonics, so the first, second, third, fourth, and fifth harmonics. So we'll have the frequencies, the harmonics, as a function of these 3 masses, which will give us the corresponding tension. So as we increase the tension, remember the wave speed is equal to the square root of F over mu. So as we increase the tension, which will also decrease mu, the wave speed should increase, which will increase all of the frequencies. It'll increase the first harmonic, and it'll increase the higher order harmonics as well. So that's the basic idea of it. And we will collect the data and then we'll have to manipulate it a little bit later. Okay, so that's the first experiment. The second other experiment, which has to get done within an hour, is we have, what the heck do we have? We have, hold on, I want to pause it while I remember what I'm doing. Okay, so the second experiment is a transformer. So what we're going to have is we're going to have a primary side and a secondary side. We're going to switch these around. So those are using those two solenoids that are inside of each other. And so we're going to measure the, well, we're going to do an input voltage, which is on the sheet, and we're going to measure the output voltage. So this is going to be using the signal generator. And this one will be measure channel A. So what we're going to do is we're going to vary the input voltage and see how the output voltage is, both as a step-up transformer and as a step-down transformer. So we'll do it both. We'll do it as a step-up transformer and a step-down transformer, and we'll end up plotting V1 versus V2, or V2 versus V1. And it should be fairly linear, but we should see maybe a factor 10 difference in voltage. So for example, when this is the higher voltage, this one is going to be, maybe a tenth of the voltage. And when this one is the lower voltage, we'll have to start off low. This might be that way. So they switch. We'll do all these at 60 hertz, which is a normal frequency that we get out of the wall. The second thing is we'll look at this step-down transformer, and we'll look at the voltage out as a function of the frequency. So we've already done 60 hertz, and we'll get some value. And what we'll find out is as we decrease the frequency, the output voltage goes down. So you need a certain amount of frequency to get the transformer working effectively. We need to generate some dpdt. dpdt is the magnetic flux is changed by oscillating the frequency, and the more we oscillate, the more oscillation we get, the more dpdt we get. So in the US we use 60 hertz. In Europe they use 50 hertz. Nobody uses anything less than 50 hertz. So that's the next thing, is we'll look at voltage as a function of frequency. And finally, we will look at how the iron core affects the output voltage. So how necessary is an iron core in a transformer? So we'll have two graphs of input voltage versus output voltage. We'll have another graph which shows output voltage as a function of frequency, and then we'll have just some general comments about how the effectiveness of the transformer is as a function of the iron core.